Hey guys, it's Professor Floyd again, and I am going to show you how to do homework set 6, question number 2. In this question, I'm asking you to calculate, to tell me what the concentration of methyl tert-butyl ether is in the headspace of the air inside the well that's just above the water if we know the concentration of MTBE in the water. So, maybe we have a groundwater contamination issue. We send a lab, they go out, they collect a sample, they pull water out of the well, stick it in a VOA vial, there should be no headspace, they analyze it back at the lab and they give us a result. And we're curious, what's the concentration of MTBE in the air just above that water sample when it's sitting in the well for a long time? So I can't use a pen, I gotta use a marker for this. So MTBE, methyl tert-butyl ether, has a molecular weight of 88.15 grams per mole. This is generally the chemical structure. So there's your tert-butyl ether. This is your ether portion, your tert-butyl. And so MTBE has sort of a peppermint kind of smell. I don't know, it's got a very distinct smell, and it's kind of pleasant and it's kind of noxious at the same time, but very different than the way gasoline smells and those kinds of hydrocarbons. So we know the concentration is 90 milligrams per liter, which this is also in solution chemistry. So liquid phases, we can express milligrams per liter as parts per million. We're not going to do that right now, but just know that maybe you will have information given to you in the solution phase as ppm, and you're supposed to know that that converts directly to milligrams per liter in mass units. So we have 90 milligrams per liter in the water, and we want to know the concentration in the headspace. But I also want you to express the concentration in the headspace in ppm. Alright, and so this is where it's important to remember that ppms for gases are different than ppms for water or for liquids. In water and solution chemistry, we know that 1 liter of water equals 1 kilogram. Therefore, 1 milliliter equals 1 gram. So when we talk about mass units, the volume here is actually a mass, right? Or it represents a certain quantity of water, which is virtually 1. And at the types of temperatures, it's 0.99 something. So it's basically 1. So we have 90 milligrams per liter. Well, we can measure water a lot more conveniently than we can mass. So we can have volumetric measures. So 90 milligrams per liter is also supposed to be synonymous with 90 milligrams per kilogram. And when you have mass per mass like that, it's dimensionless. And that's why we call it parts per million. You've canceled out the 2 dimensions. You have a mass divided by a mass. But that's not true parts per million. Parts per million, as the name would imply, it's this part versus this part. And so if you want to think about gases and molecules as particles, then gas phase parts per million is really more accurate, because gas phase parts per million is we have a bunch of gas. They're all independent particles. And then we have a few parts that are some other chemical. And so for every million parts of the black dots, we have 5 parts that are the green dots. So it's truly a part per part, and molecular weight isn't going to change that. It's a molecule of this and a million molecules of something else. So you have to just be aware of that, and that's one reason this question is being asked of you. So you're given 90 milligrams per liter in the water. We're going to use our Henry's law constant. We need to look that up. So the constant of Henry is equal to, NIST is a good resource for that. They give 2 on this one, 1.6 and 1.7 moles per, they say kilograms, but I automatically convert that kilograms to liters because it's water, liters and bar. So we take that and we multiply that by our pressure. Oh, sorry. The Henry's law constant is that. So we know that the concentration in the water is equal to the Henry's law constant multiplied by the pressure. So in this case, we know this one and we know this one. So we're going to solve out for our pressure. So just bring the KH underneath. So our pressure equals our concentration, which is 90 milligrams per liter, divided by our Henry's law constant, which is 1.6 moles per liter bar. So I like to go ahead and get all my units in simplified form first. And so these liters per bar move up to, actually, we can go ahead and cancel our liters here. And we know that the bar is going to move up to our numerator. So our units will be milligrams bar per mole. And we're looking for parts per million. So we need to get rid of all of our units to express this properly. So 90 divided by 1.6 milligrams bar mole. Alright, sorry that's kind of taking me a while, but we'll move on with it. So we get rid of our moles simply by multiplying 1 mole is equal to the molecular weight, 88.15 grams. Of course that doesn't get rid of our milligrams, so we still got to convert that 1 gram is equal to 1,000 milligrams. So that will cancel. Our moles cancel. Our milligrams cancel. Now we're left in bar. And so we just get rid of our bar by saying we've got this many bar, and that's out of how many bar in the environment. So I don't actually know that offhand. I think it's 1.01 something, but because I don't know it and I don't want to stop the video to look it up, I'll just go into torr and then convert, because I know that there's 760 torr in the atmosphere. So 750 bar per 750 torr per 1 bar, and then I know that the atmosphere as a whole is, well, sorry, so that gives me my pressure. And I'll calculate that out real quick. So that's my pressure in torr. So 750 divided by 1,000 divided by 88.15 divided by 1.6 multiplied by 90. So we did a lot of dividing there, and we come out to 0.48. Right, so 0.48 torr, and if we want to know that in parts per million, we know that we have 0.48 torr out of the entire environment, which is 760 torr, and then if we multiply by 1,000,000, that will give us parts per million, right? That puts us in the parts per million. So so that divided by 760 and times 186. So 629.7. So 630 parts per million will be our concentration in the air. Just kidding, I didn't actually end it yet. Now I'll end it.